All right, today we're looking at graphing two variable linear inequalities. All right, and we're going to start off by reminding ourselves how we graph a linear equation that's in slope-intercept form, as we see over here at the left. All right, we see we've got y equals negative 2x plus 3. Let's just give ourselves a little bit of a refresher here. We know that this is our slope, and this is my y-intercept. All right. Why is that important? Because when I go to graph, now all of a sudden I can come over here and I can use that information starting with the y-intercept to plot my first point at 0, 3. All right. Once I get that point, I can now come back to my slope and I can use my slope to move. Well, we've got a negative 2 for my slope and all whole numbers can be placed over 1. So this reads as down 2 over 1. And we always go over to the right. We move from left to right, just like we read from left to right, and we write from left to right. So if I do that, moving from here, I'm going to go down 2 over 1. That's this point right here. Down 2 over 1. Down 2 over 1. And I'm going to continue to plot all of my points that I can find on this graph here. And I'm going to go backwards as well, reverse both directions to continue this line in both directions. Now, is this do these points represent all the points that are solutions to this equation? No. These are just some of the solutions to this equation. Any one of the points that I just plotted, if I were to put it into this equation, it makes my equation true. And just to prove that, I'm going to come over here. Let's just pick a point. We're going to go with 1, 1 right there. All right, so if I put 1, 1 into this equation, that means I'm going to put 1 in for y equals negative 2 times 1 plus 3. All right, and if I simplify that, I get negative 2 times 1 is negative 2, plus 3 is 1. It works. It makes it true. Let's take a look at another one. What if I do this one? 4, negative 5. All right, so if I go 4, negative 5, and I plug that in, that means negative 5 is equal to negative 2 times 4 plus 3. And negative 5 is equal to negative 2 times 4 is negative 8. Negative 8 plus 3 is indeed negative 5. It makes that true. All of these points make this equation true. That makes them solutions to that equation. That's why we're representing them on the graph. We're trying to represent the infinite number of solutions that make that equation true. We can't do it with just these points, though, because there's more than that, and they go beyond our screen, but they also go in between every single point here. All right? So as we look at this, make sure it's in black there, that means that I can draw a line that connects these points, and that line represents every single solution to that equation. Any point on that line is a solution. And that means I can use this line to identify these points. What if y is 8? Well, if y is 8, then that means that x is about negative 2.5. All right, so negative 2.5, comma 8 would be a solution to that equation. All right, and every single point on that line would make this equation true. That's where we're starting, okay? Now, if you have any questions about that and you don't understand that, please go back, watch some of my other videos, or come talk to me, all right? Because we need to take this concept and now go one step further. What if I change this equation now to an inequality? Now, all of a sudden, instead of having y equals negative 2x plus 3, I now have y is greater than negative 2x plus 3. Y is everything that is equal to that line and greater than it. All right, well, where do those points exist? Well, you could start picking some points. Try one out. Let's try this point right here. I'll just pick that point, 2, 5. Does 2, 5 make this equation, inequality, true? All right, well, if I take that and I plug in 5 in for y, it's greater than or equal to negative 2 times 2 plus 3. I find that 5 is greater than or equal to negative 2 times 2, that's negative 4. Negative 4 plus 3 is negative 1. Is 5 greater than or equal to negative 1? Yes, it is, so that's true. Let's test another point. Let me just pull another point up here. Let's go for that one right there. All right. So now we're testing 8, 1. So if I plug 8, 1 in here, that means y is 1. So 1 is greater than or equal to negative 2 times 8 plus 3. Well, that is 1 is greater than or equal to negative 2 times 8 is negative 16 plus 3 is negative 13. Is 1 greater than or equal to negative 13? Yes, it is. I'll put a check mark up for that one too. All right, yes, it makes my equation true. That's another one that makes it true. In fact, all of the points over here, all of these, oh, I'm erasing now, there we go. All of these points, any one that you choose to put over here, these would all make my equation true. Every single one of these are solutions to the equation because every single one of these would give you a y value that is greater than or equal to negative 2x plus 3. Negative 2 times the associated x value and so on. But notice where I'm not putting points. All right, I'm going to change my color. Notice where I'm not putting points. What about a point over here? What about that one? Let's take a look at it, see what happens. If I have a point over there, let's plug it into my inequality here. Let me make some room. I'm just going to erase this one here. All right, and if I plug in negative 4, 1, that means 1 is greater than or equal to negative 2 times negative 4, always putting y in for y and x in for x, plus 3. Well, that means 1 is greater than or equal to negative 2 times negative 4 is positive 8. 8 plus 3 is 11. Is 1 greater than or equal to 11? No, it is not. 1 is less than 11, so that does not make it true. So this was not a solution, which is why this is not a point on my graph. Now, why is this the case? Well, let's take a look at what we're really understanding here. When we said that y is greater than or equal to negative 2x plus 3, well, this line here represented every single point where y was equal to negative 2x plus 3. And my y-axis is this axis right here that goes up and down. All right, that's my y-axis right there. All right, so this is what I'm looking at to refer to, and I'm going to change my color so we can now see how we react to it. If that's my equal point, and I'm looking at the y-axis, where is y greater than that line? Well, greater than, if I just look on the actual y-axis itself, greater than is above. All right, all of these points above. Here's 3. Greater than 3 is 4, 5, 6, 7, 8, 9, 10, 11, 12, everything above. Now, it's not just on the y-axis, but it's everywhere above that line. Go anywhere on that line. If I start right here, where is y greater than that line? Well, y is greater than above this region here. Y is greater than above this region here. Y is greater than above this region here. In fact, if you put anywhere in this line, y is greater than above. Sorry, I went over my line a little bit. There we go. Y is greater than above this line. That means this section in here. And we start to get this entire section covered that all represents every single point that is above my line. All right? And this is how we show it. We draw our line, and then we can shade that entire section above that line when y is greater than. Okay? Now, you don't actually have to darken it. Do not scribble it. Don't make it a mess. Oops. Don't make it a mess as you do it. Please make sure that your shading is not super messy. There are ways to go about shading it, and we'll show you those that make it nice and neat. Let's change some things up now. What if my symbol was not greater than, but rather what if my symbol was less than? How would this change things? Well, it would now change it so that our solution, instead of being above the line, now less than. So look at my line. Here's equal. Less than is below that line. Less than is below that line. Any point in this region would make that true. And we can show this with shading that looks like this. You can draw lines away from our reference line, or boundary line as we'll come to call it. All right, you can draw them perpendicular in the opposite direction, so they're just going away from there. All right, and that's our line right there in our shading. Okay. So then this whole region represents solutions. And once you've done that, I recommend that you test a point. Pick any point in that region. The easiest point to pick is always 0, 0. Pick that point 0, 0 or any point on the y-axis and see if it makes it true. All right, is 0 less than or equal to negative 2 times 0 plus 3? Well, the reason I chose 0, 0 is because it makes this x value 0, and that's really easy to calculate because negative 2 times 0 is 0. So I'm really just looking at is 0 less than or equal to 3. That is true. Therefore, this point right here needs to be in our solution region, which is where we shade, and that is true. All right. If you pick a point, let me just pick another one here. I'll go for green, just so you know that it's not there. All right. Let me pick 0, 7. All right. And if I test that point, 0, 7, that means 0 is less than or, sorry, not 0 is less than. 7 is less than or equal to negative 2 times 0 plus 3. And that means that 7 is less than or equal to 3, and that is not true. All right, that's a contradiction. That's what the symbol means. That is not true. Therefore, this is not a solution, so I should not be shading that side. That's what you can do. You can always read the inequality. Less than is below your graph. Greater than is above your graph, but then test a point to make sure you shaded it on the right side. What if it changes one more time? What if instead of having y is less than or equal to, it's now just y is less than? Take a look, I changed that symbol right there. Y is less than. How is that going to change our graph? Well, I want you to consider what we had before this. Before this, we were working with a number line, and I'm just going to use this number line right here. The x-axis is my number line. And let's say we had something like x is greater than or equal to 14. Well, that means I put a point at 14, all right, and I shaded everything greater than 14. All right, and we used something we called a closed circle, all right? But what if I now change that? What if I came back and I said, well, I don't want it greater to, and I don't want it greater than or equal to. Now I just want it greater than. Well, that came back and that changed this point. All right? Now instead of a closed point, we had an open point. An open point representing that it was everything up to but not equal to that point. Same thing's going to happen here. On a linear inequality, we've got our solution region, we've got our boundary line or our reference line. All right, we're going to call this our boundary line, also referred to as a reference line because it marks the boundary between solutions and not solutions. And a solid line means that it can also be on that line. It's allowed to be equal to that line. So instead of a solid line, we are going to come now and we are going to make a dashed line or dotted line when it is not equal to. All right, and that's how we represent an inequality where it's not allowed to be equal to that line. It's everything up to, but not including that line. So let's summarize all of this with our final notes. Here's your notes on graphing inequalities. All right, taking a look at this, we see that we have, let me pull this up here. All right, if something is less than or greater than, all right, but not equal to, we have ourselves an open circle or an open line, all right? Open circle or open line. If something is less than or equal to or greater than or equal to, we then have to conclude those boundary points or boundary lines as part of the solution. Remember, shading is always solution, so therefore we fill these in. They are filled in completely there. It's a nice solid line. How can you remember that? Well, look at the symbol. Look underneath the symbol. I've got a solid line under the symbol, therefore a solid line on my graph. Okay? Now let's look at our solution region over here. All right? My solution region, all right, if I have something that is less than, all right, then I'm going to be shading to the left on a number line or below my graph on a two-dimensional coordinate grid. If I have something that is greater than, then I'm going to be shading to the right of our boundary point on a number line or above my boundary line on a coordinate grid. All right? And these symbols over here, all right, this whole row right here, these symbols represent shading above or below that reference line. If you look at it, all right, we had a nice angle here, all right, and the shading was below that line, right? That's what we see right here. We have our nice reference line or boundary line there, and shading is below that line, okay? That's why this symbol represents below. Above, here we have a nice boundary line, and shading is above that boundary line. That's what the symbols represents. These symbols are actually the symbols that you can use in your graphing calculator when you go into the y equals section. You'll see in there, you'll see y1 equals, and then you can put in your equation like 2x plus 3, and over to the left, all right, there's usually just a line. They usually just have a line like that. But if you go over to that line, use your cursor, move it to the left, and you hit enter on that line twice, all right, it actually becomes this one right here. It becomes this one right here. All right, that's if you hit it twice. And if you hit it 3 times, it becomes this symbol right here. All right, and these symbols, you can then put inequalities in your graphing calculator to represent less than. All right, these ones are the below the line here is less than, all right, and greater than. And then you can actually get graphing inequalities on your calculator.